All right, so in this lesson, section 3.2 is on continuity. Basically, what we're trying to figure out is our function continuous? Is there a way to determine if the function is continuous or not? If our function is continuous, it opens up a whole lot of new things that we can do and we can conclude just by knowing if it's continuous or not. So we're going to have a definition here of continuity. It says a function f of x is continuous at x equals c if the following hold. We got three conditions. First, our function must be defined. If our function is not even defined at that value, we're done. Next, the limit has to exist at that point at x equals c. So in other words, the limit from the left must equal the limit from the right. The third condition is we're putting both of these first two together. The limit as x approaches c must exist and it must equal our function evaluated at c. If f of x is continuous at c, then there are no breaks, jumps, holes, etc. at x equals c. There could be stuff out other places, but not at this point. To see some graphs of this, see the PowerPoints. In the PowerPoints, there are graphs and everything that you can see. I did not convert them over into here, but check the PowerPoints inside of Canvas, and you'll be able to see them there. So continuity of functions. So the first thing that we need to talk about is polynomial functions. All polynomial functions are continuous everywhere. I don't care what C is, they are continuous everywhere because polynomials are polynomials. They are easy. They're fluid and everything. So an example of that, x squared plus 25. What that graph looks like is if we're way up here at 25, then our graph looks like this right here. There's no holes, there's no jumps, there's nothing in that. The big one where we have to figure out if we are continuous or not is rational functions. Rational functions is one of the biggest pieces that we try and figure out if they are continuous or not. Rational functions y equals p of x divided by q of x are discontinuous at all x such that q of x equals 0. So in other words, check to see where the denominator equals 0 and solve that, and that will tell us where our function is discontinuous at. So in this first case, x plus 1 times x minus 5 divided by 2x plus 1 and times x minus 1. Easy way, take 2x plus 1, set it equal to 0. Take x minus 1, set it equal to 0. So at x equals 1, and then 2x equals negative 1, x equals negative 1/2. So at x equals negative 1/2 and x equals 1, it is discontinuous. For the second one here, 5 plus x over x times x plus 4, we set x equals 0, x plus 4 equal to 0. So x equals negative 4, we're discontinuous. X equals 0, we're discontinuous. These are what we call as non-removable discontinuities. In other words, nothing we could factor out of the numerator and cancel out in any case. Now, for this one, this is x squared minus 16. So that's going to be x plus 4, x minus 4, all over x minus 4. I'm factoring this just to show you that it is removable, but we still do the same process. X minus 4 equals 0. So x equals 4, and this one is removable. It's removable because x minus 4 could cancel out. That would leave us with a hole in our graph, but it is still a removable discontinuity. For this one, f of x equals x cubed minus 2x. Sorry, the absolute value of x cubed minus 2x over x minus 10. We still set this equal to 0, so x equals 10 is our discontinuity. X cubed minus 2x is x times x minus 2, or x squared minus 2. None of that would cancel anywhere, so therefore x equals 10. Now, piecewise functions are a little bit different. The possible x where f of x might be discontinuous are at breaking points. So we need to check to see if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c to the right of f of x. So to do this, I'm going to label this as equation 1, equation 2, and equation 3. So I'm going to plug in, and I got breaking points at 2 and at 4. So I'm going to create kind of a little chart over here. So I'm going to have a 2 and a 2. I'm going to have a 4 and a 4. Oh, let me erase this line. A 2 here and a 2, 4. So this is for equation 1, this is for equation 2, and this is for equation 3. Yes, I know it says less than 2. We're going to violate that in this case by just plugging it in. So when we plug 2 into that first equation, it's a constant function, we get 1. When we plug 2 into the second one, we get 2 plus 3, which is 5. We plug 4 into the second one, we get 4 plus 3, which is 7. We plug 4 into the last one, we get 7. So what we're looking at here is we need this value and this value to be the same, because when we plug it into equation 1, it must equal when we plug into equation 2. 1 does not equal 5. So therefore, we have a discontinuity or in other words, it's discontinuous at x equals 2. We're only looking at the x values where it's discontinuous. Now, for the second one, we need 7 and 7. For equation 2 and equation 3, we get that. So it's only discontinuous at x equals 2. So we're going to do something very similar in this case right here. Again, we got equation 1, equation 2, and equation 3. So my breaking points are at 1, 1, 3, and 3. So my first one is for equation 1. My second 2 are equation 2, and my last one is equation 3. So when I plug 1 in the first one, I get 1 plus 1, which is 2. When I plug it into the second one, I get 1 minus 3 plus 4. So 5 minus 3 is 2. Excuse me. We plug in 3. Second, we get 9 minus 9 plus 4. So we get 4. We plug in 3 into the last one. We get 8 minus 3, which is 5. So in the first case, we get a 2 and a 2 when we plugged in 1 in both cases. But in the second case, we plugged in, got a 4, we plugged in a 5. So we are discontinuous at x equals 3 would be our answer here. So discontinuity has a lot to deal with our values here and being able to see what's going on and everything. So discontinuity is a little in depth in terms of graphs. We got to look, see where we have jumps, discontinuities, holes, breaks, etc. But in terms of our whole entire stuff, it's not that bad. Make sure that you look at the PowerPoints in order to see some of the true graphs and everything.